Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah, amma ba'd. So everyone, welcome back. I'm going to start back on GNAV and do the, I guess, I did 10 questions last time. Let's see how I get on if I do those again. Let's see, where is the window? There it is. Okay, so I've got GNAV open, select topics, charts, sequentially. Let's do the first 20. So generate exams, start. So this question says a polar stereographic chart is used for navigation. A straight line between 75 south, 166 east, and B 78 south, 154 east is drawn in this chart. The true track, so 166, 154. So going out from the out inwards, from the outside inwards. So going from 166, which is going to be lower down, going upwards and inwards. 154, the true track of and we had another thing open about that before. Yeah, here we go. 166 to 154. Anyhow, the true track angle of the run line is 223. Calculate the direction true of the straight line in position B. And I think we did that with the conversion calculation, yes. So we said the difference in longitude is 12. That's the change in longitude times the sine mean lat, 76.5. Gave us a conversion angle, 223 plus 5.83 is 229. All right, great. Just so I don't neglect anybody, I'm going to open this window, a new copy shortcut. Put this here. Okay, got 0 watching now, that's fine. No big deal. Switch account, and that's going to be fine. There we go. Great. So a route is flown from 85 south, so staying on the same latitude, from 100 east to 140 west. That's going to go over the timeline, isn't it, of the anti-meridian, of the Greenwich anti-meridian. So at 160 east, the grid track and true track on a polar stereographic chart with the grid oriented on the 180 meridian are respectively. Have anything there showing that? Not really. I thought I did that last time. Since I didn't save it, then yeah, so we've got 100 east at 160 east. If we're going sort of, the true direction is going to be 090 approximately for a run line. At 160 east, the grid track and the true track on a polar stereographic chart. Okay. Respectively. Actually, the way I'll do it is as follows. New slide. I would say 100 to 140. The true track is going to be Yeah, it's going to be more or less. And the southern hemisphere is going to be more than 90, isn't it? So if we look at this, this would be a southern hemisphere type picture. So if that run line going to the east, going this way, would be 090, then the run line at 160 would be one. Is 160 more than halfway across? It would be starting at the run line would be 090. The track would be greater than 090. Midway it would be 090, and midway would be 100 plus 140. So 40 plus 80, 120. Half of 120, 60. So 160. So halfway, I'd expect the true track to be 090. Good. And the grid track, what's the grid track going to be? The grid track is going this way, like downwards. Well, that's the orientation of the meridian. So grid track would be something like 270. So 90 and 270, is that there? 90 and 250. All right, so grid. So 90 is true. 250 grid. Yeah, I bet that's wrong. Actually, 70 grid and 90. Why would it be 70 grid? What's the orientation of the grid oriented on the 180 meridian? Okay, let's see. So the track there's 160. That's 70, that's 90. Okay, fair enough. Next. I'm not a fan of those polar stereographic questions. A VOR is situated at position 74 north, 94 west. Local variation is 50 west. '94 west, 50 west. Okay, polar stereographic. Proceed along magnetic radial 238 inbound. An aircraft has to follow a grid track of, so 94 plus 180 is 174, isn't it? No, sorry, 274. Hold on, let me calculate on the calculator. 94 plus 180, 274, yeah. Proceed, and then we want to do the what's the question? 74 north, 94 west. '74 north, 94 west. This might be the wrong one. Okay, so a VOR situated at position 74 north. Go down here. So let's draw a circle. If that's that circle is 74 north, then we draw VOR 94 west. So VOR is going to be, if that's the middle, what are we, north? So the Greenwich mean line is there. That's northern hemisphere. 94 west. It's just more than 90. There we go. So the VOR is located here. Okay, 94 west. Polar star justified with Greenwich grid is used for navigation. To proceed along magnetic radial 238 inbound, an aircraft has to follow a grid track of 238 inbound. So what would be 238? 238 would be something like that, a radial going in that direction. That's 270, that's 250, that's going to be more like this. Let's do that. Okay, that would be magnetic though. So magnetic inbound, 238. So if we take the variation west magnetic best, 238 plus 50, 288. Or are we taking away because 238 is the magnetic one? Yeah, so take away the 50. So 238 minus 50 is 188, which means the line would be more like that. True. Well, if it's true, it would be true based on this. So 238. So this is north now, isn't it? That's 0, 0, 0. So 238 is actually more like that. And then we take away the 50, we get 188. So actually that's going to be like that. So the true track would be 188 plus, what would be, it's going to be 008 approximately. 008 inbound, because the reciprocal of 188. And the grid track is going to be, which way is the grid track oriented? Greenwich. Okay, so that's going to be just over 90. So a grid track of, this is all wrong. So just over 90 is 103. That's right. Okay. Let's look at the picture. So they showed, there's the grid meridian, that's correct. 94 is this line, the red line here. And 238 would be, which way? Oh, that blue line would be 238, would it? Well, for magnetic, yes. Oh yeah, 008 is the reciprocal. Yeah, okay, fair enough. Route A to B is drawn on a polar stereographic chart with the grid aligned with the Greenwich meridian. The true track of the straight line at A, 75 north, 10 west, is 80 degrees. Okay, let's do this. So if we say this is 75 north, 10, the true track of a straight line is at 10 west, at this location, 10 west, is 80 degrees true track. Okay, so 80 degrees. That would be something like 90. So we'll say 80. Let's just draw it like that. Let's say that's 80. So what's the grid track when passing the meridian 50 east? Which way is the grid oriented? Grid aligned with the Greenwich meridian. Okay, so the grid is like this. And the grid track when passing the meridian. What's the grid track when passing meridian 50 east? So let's see, where is 50 east? 50 east is going to be just over halfway. What's about there? So if that's the meridian for 50 east, the grid track, if we're going in sort of easterly direction, the grid track would be something like 90 degrees, right? That and that. So this track here, something like 90. That's about 90 degrees, isn't it? Let's say 90. Yep, that's right. Alhamdulillah. 90 degrees. Good. Next. So now we've got a scale question. At 47 north, the chart distance between meridians 10 degrees apart is 12.7 centimeters. The scale of the chart at 47 north approximates. So we're going to say 10 degree meridian. It's going to be 10 times 60. I think we did that before, yeah. So yeah, 10 times 60. Using the departure formula, right? Could do that again down here just in case, just to test our memory. So Chalong times the departure formula, sorry, departure equals Chalong times 60 times, well actually we do it like this, Chalong 60 times cos lat, cosine lat. And departure, do we have a departure there? No. So we're going to say departure equals 10, 60 times cosine of, what's the latitude? 47 north. Cosine 47. Departure equals 600 times cosine 47 is 0.6868. So times 600 is 409. 409 nautical miles. The scale of the chart at 47 degrees north. Okay, so now we want to convert this into centimeters. So 409 times 1852 times 100 for centimeters equals 1852 times 100. That's about 76 million approximately. Okay, so that's centimeters. And we want to divide that by 12.7. So 76 divided by 12.7 centimeters equals approximately 6 million. So the answer is 1 to 6 million. Next question. A straight line drawn on the chart measures 4.63 centimeters and represents 150 nautical miles. The chart scale is 1, so we're going to do this again. 150 nautical miles. So we'll skip all of this bit up here. We'll just do 150 nautical miles. So 150 times that equals 150 times 1852 times 100 is about 28 million. 28 million. So what was the scale? 4.63 centimeters. So we'll do that divided by that's also 6 million. Good. Chart scale is 1 to 1,850,000. So we're going to do some reverse engineering on this one. The chart distance between 2 points is 4 centimeters. So if this is 4 centimeters, and this is 1,850,000. So we're going to say this times 4 equals 7,400,000 centimeters. Let's put, and what they're asking us here, the Earth distance. Okay, so we're going to convert these centimeters. So we're going to divide by 100 and divide by 1852. That gives us an Earth distance of 39.9568. So that's going to be about 40 nautical miles. Is that an option? Yes, it is 40 nautical miles. Great. A straight line on the chart, 4.89 centimeters long, represents 185 nautical miles. The scale is, so 4.89 centimeters up here. And we had 185. So if that's 185, 185 times 1852 times 100 is 34,262,000 centimeters. And yep, so we're going to divide that by 4.89. That's 70 million. Sorry, 70. Sorry, 7 million. Hold on a second. 1, 2, 3, 1, 2, 3. That's 7,006,543. 7 6,543. Okay, so that's the scale. So 1 to 7 million. Good. Constant of a cone of a Lambert conformal conic chart is quoted as 0.3955. At what latitude on the Earth on the chart is Earth convergency correctly represented? What latitude on the chart is Earth convergency correctly represented? Okay, let's see. If I was to say 23, let's say sine 2318, that's 0.395. That's it. So what I just did is I said sine 23. I don't know how to do the degree symbol up here. 23. Let's do use an apostrophe. 2318, and that equals 0.3955. And that's the answer. So the first one was correct. The distance measured between 2 points on a navigation map is 42 millimeters. The scale of the chart is 1 to 100. So if we say this answer here is 1,600,000. Okay. How many centimeters? Oh, 42 millimeters. So it's going to be 0.44 centimeters. Actually, that's this answer here. So that scale. So I have to say 1,600 times 0.44 equals, okay, let's try that. 1,600,000 times 0.44 is 704,000 centimeters. Convert that. So we're going to say divide that by 4 divided by 100 divided by 1852. So divide by 100 divided by 1852. That gives us an answer of 3.8. 3.8 nautical miles. The closest is 3.69 nautical miles. No, that's wrong. It was actually 36.3. Okay, so I screwed up with the millimeter. So let me do that again now. Instead of 0.44 centimeters, I should have said, let's try 1,600,000 times, let's just say 44 millimeters. Times 100, that would be, is it times or it would be divided by, sorry, divided by 1. Actually, millimeters would be, is that 1,000? No, that brings us to the same place. So 1,600,000 divided by 44 millimeters times 44, sorry. Divided by 1852. And divided by 100 gives centimeters. Divided by 10 to give millimeters. Okay, so that's 38. So like they've shown here, 42 millimeters. So 1,600,000 times 42 millimeters is an Earth distance of 67,200,000 millimeters, which equals 67.2 kilometers. Okay, and you can do that on the navigation computer. Oh, I'm very sleepy all of a sudden. On the Lambert conformal chart, the distance between meridians 5 degrees apart along latitude 37 degrees north, Lambert, okay, that's there's polar, Lambert, and then there's Mercator, isn't it? All right, so Lambert is the one at a sort of angle, not from the top, is in between. On a Lambert conformal chart, isn't it a conical chart? The distance between meridians 5 degrees apart along latitude 37 degrees north is 9 centimeters. Distance between meridians 5 degrees apart along latitude 37 north is 9 centimeters. Okay. Scale of the chart at that parallel approximates 2. So we can do departure formula again, shall we? If we say departure equals Chalong 60 times cos lat. So any Lambert conformal chart distance in meridians 5 degrees apart along latitude 37 north. So we're going to say departure equals 5 times 60 times cos 37. Departure equals 300 times cos 37, 0.79. So let's say 0.8. Otherwise, 0.7986 times 300. It's 239, 240. Departure equals 240 nautical miles. All right. So 5 degrees departure is 9 centimeters. So the scale is 240 times 1852 to get kilometers times 100 to get centimeters equals 240 times 1852 times 100 is 44.5 million. So 480 centimeters. And the scale, 5 degrees is 9 centimeters. So divide that by 9. So 49,387. So that's about nearly 50 million. Let's just say 50 million. What's our answers here? 50 million? Sorry. 1, 2, 3, 4, 5. There's 5 million, sorry. There's 5 million. Good, got that. On a direct Mercator projection, a particular chart length is measured at 30 degrees north. What Earth distance will the same chart length be measured at 60 degrees north? The Earth distance will the same chart length be on a direct Mercator projection, a particular chart length is measured at 30 degrees north. Okay. What Earth distance will the same chart length be if measured at 60 degrees north? It will be less, wouldn't it? Yep. On a Mercator projection scale, scale expands as latitude increases, which means that a given chart distance will represent a smaller Earth distance at a higher latitude. Yeah. On a chart, a straight line is drawn between 2 points and has a length of 4.63 centimeters. What's the chart scale if the line represents 150 nautical miles? So if we were to say 150 at this bit, actually let's do it down here, 150. So we'll just say 150 times 1852 times 100. That's 28 million. It's actually 27,780. And we will, what was the centimeters? Divide that by 4.63. That's 6 million. On a chart, the distance along a meridian between latitudes 45 north and 46 north is 6 centimeters. Okay, 45 and 46, that's 1 degree of latitude. The scale of the chart is approximately. So 1 degree is 60 nautical miles. So 60 nautical miles times 1852 times 100 is 11,112,000 centimeters. Divided by 6. That's 1,852,000. Scale of the chart is approximately C. Yep. The chart has a scale 1 million, 1 to 1 million, from A to B on the chart. From A to B, the chart measures 3.8 centimeters. The distance from A to B is in nautical miles, so we'll go backwards this time. So we'll say 1 million times 3.8 divided by 100 divided by 1852. That's 20.5 nautical miles. C is correct. Approximately how many nautical miles correspond to 12 centimeters on the map? How many nautical miles correspond to 12 centimeters on a map with a scale? Okay, so we'll reverse this again. So 2 million this time. So let's do it on here actually. So I'm using my physical calculator rather than the digital one. So let's say 2 million times 12 divided by 100 divided by 1852. 130 nautical miles. There we go. That's good. Alhamdulillah. If in a navigation chart, a distance of 49 nautical miles is equal to 7 centimeters. In a navigation chart, a distance of 49 nautical miles is equal to 7 centimeters. Scale of the chart is approximately the same thing again. So 49 times 1852 times 100 equals million. Which is not there. Let's do that again. 49 nautical miles times 1852 times 100, 9 million. Okay, and divide by 7. 1,290,000. So 1,300,000. That's here. If the chart scale is 1 to 500,000, what Earth distance is represented by 7 centimeters? So we'll say 500, 1, 2, 3, times 7, divide by 100, divide by 1852. So our Earth distance is 19 nautical miles, approximately, which is not there as an answer. So we have to convert this to kilometers. So times 1,852. No, actually 1.852. It's 35 kilometers. It's not there. Oh yes, it is 35,000 meters. Okay, so times 1,000. 35,000 meters. That's the correct answer. Given, direct Mercator chart with a scale of 1 to 200,000 at the equator. Okay. Let's say that again. Direct Mercator chart with a scale of 1 to 200,000 at the equator. Chart length from A to B. At the equator. Chart length from A to B in the vicinity of the equator is 11 centimeters. Okay. What's the approximate distance from A to B? Okay, so we'll do that again. So 200,000. What am I doing? So we'll say 200,000 times 11 divided by 100 divided by 1852 equals 12 nautical miles. Good. Chart distance between meridians 10 degrees apart at 65 latitude north. Okay, chart scale, so we need to do departure again. So this time I'm going to say cos 65. Cos 65 equals what? Doesn't work. So let's do that again. 65 cos. There we go. 0.42. 0.42. 10 degrees times 60. 600. So we're going to say 0.42 times 600. 254 nautical miles. What do they want? The chart scale. Okay. So we're going to say times 1852 times 100 divide by 9.5 is nearly 5 million. Alhamdulillah. Good. So let's see which questions did I get wrong. 4 questions wrong. Are you kidding? What did I get wrong? The route is flown from 85 south. Okay, at 160 as halfway, the grid track and true track on a polar stereographic chart with a grid oriented from 180 meridian are respectively. So it's going to be true track is going to be 90, isn't it? But the grid track, if it's on the 180 meridian, okay, then that's upside down. Yeah, 70. The distance measured between 2 points on a navigation map is 42 millimeters. Oh yeah, we saw this one before, so let's do this again. So we've got 1,600,000. What's that, centimeters? Is that millimeters? Let's just assume it's centimeters. We'll multiply that by 42. We'll divide by 1,852. And divide by 1, that's centimeters. Divide by 10 for millimeters. So 36.285, 36.3. Correct. A straight line from 120 to 160 east at 75 degrees south is drawn on the polar stereographic chart. When passing meridian 155, the true track is, so we've got 75 south. $120 east to 160 east. Let's move this stuff out of the way. South, if we're south, it's going to be like this, looking up at the Earth. Now again, 120 east to 160 east. So 120 east is going to be like, that's 90, 180, that, let's say 120. Let's just put that here. We'll do another one going from 120 to 160. So the line of travel is like that. All right. Curved line is the run line. The straight line is the track line. So when passing meridian 155, the true track is, okay, so we want the convergence angle. So if we say 160 minus 120 is 40. It's just, so we'll say convergency equals, let's this along here. So convergency is, what was it? Change of longitude, Chalong times sine mean latitude. Convergency equals, Chalong is 40, and the sine mean latitude is, what was the mean latitude? 75. Okay, so 75 sine 0.966. So let's multiply this by 40. That's 39. So convergency is 39. And if we want the convergency angle, that's 39 divided by 2. Divided by 2, 19.3. if the run line is 270, because it's the same latitude. Run line is 270. The DI D. So going westbound in the southern hemisphere. Is it southern hemisphere? Yes. South, that direction in the southern hemisphere. Actually, that line should be below. Okay. Yeah, that's right. True track. 270. It increases. So initially the track would be 270 plus 19. No, minus 19. Oh, dear. 270 minus 19. It would end. What's the question asking? When passing 155. So it's going to be. Okay. It'll be more than 270, isn't it? There's nothing there that's more than 270. At 155, the true track. If this is 155, let's say that's 155. Okay, that angle is less than 270. It's 255. No, 075. Why is that? Because the southern hemisphere. Okay. So that direction is not 000. That would be 180. So that's going to be greater than 90. Greater than 90. Oh, it's less than 90. Oh, gosh. I don't know, mate. I'm lost. Thought I got it, but I didn't. So I got the drawing correct, but the angles were wrong. I was using an isosceles or something. I'm so sleepy. So the question is asking what? True track. Okay, so 180. One large triangle is formed between the points of departure and arrival and the South Pole. Okay. True track measured at A equals 180 minus 170. So there's that track. 180 minus 70. 110. Yeah, southern hemisphere, that looks right. So it's going to be increasing and then decreasing. So it starts off at greater than 90, ends up less than 90. It's less than, okay, that's 75. All right, got that wrong. I was oriented upside down. What are the initial true course and distance between positions? Refer to image. I don't remember doing this question. Okay, this must have come later. Let's just click. What are the initial true course and distance between positions? 58, 66. We'll do that later. I think I'm going to stop now. I need to sleep. I'm really sleepy. Thanks for watching.